Well, in the previous videos we had looked at, we had determined that when we have a function that came to a derivative equal to 0, we found that when the derivative changed from negative to positive, we had a relative maximum. And then when it changed from positive to negative, we had a relative maximum, relative minimum, relative maximum, in that order. So we formalize this in what we call the first derivative test. And this time we expand out our ability to use the test for functions that are not only horizontal tangent lines, but what happens if the derivative is undefined at a certain point. Well, we say any place where we've got a critical number of a function, where the function itself is continuous on the open interval I that contains some value c, and if f of x is differentiable on that interval. So we have a couple of conditions that we need to meet, except possibly at that point. Then we can classify f of c as either a relative maximum, relative minimum, or neither a maximum or minimum as follows. If f prime changes from negative to positive at that point c, we have our relative minimum at the point c f of c. F prime of x, if it changes from positive to negative, at that point c, we've got a relative maximum at the point c f of c. And then finally, if f prime of x is both positive on the left and the right of that value c, or both negative, then we can say that f of c is neither one of those, either relative maximum nor relative minimum. So as an example, let's consider a function like this one. Our first job is to do the following. We're going to find any critical numbers. Our second job is to find any open intervals on which the function is increasing or decreasing, and then use our first derivative test to identify all those relative extrema. And the thing that we're going to do right here is that we don't even need a graph to carry this one on. First of all, f of x is a continuous function over all real numbers. So we're not even going to worry about some closed interval where the function is or is not continuous. We know that it is continuous. So the next question we might ask is, let's find our critical numbers, right? F prime of x is what we need to do that with. So f prime of x, if we take our derivative, gives us 4x to the third minus 32. All right, f prime of x equals 32. Well, this is where we're going to have to remember a little bit of algebra. Our critical numbers occur where either f prime is equal to 0 or where f prime is undefined. Well, there are no points where f prime is undefined. 4x cubed minus 32 is defined everywhere. But there's at least one point where 4 times x cubed minus 32 is equal to 0. And we can find this point by factoring. We could say, well, 4 is multiplied by x cubed minus 8. And then finding that, well, 4 would be multiplied by the quantity x minus 2 times x squared plus 2x plus 4, right? Remember our factoring the difference of 2 cubes. This applies here. This first function, x minus 2, we set that factor equal to 0, and we find that x equals 2 gives us a point where the derivative is equal to 0. If we were to take our other factor, our quadratic factor, x squared plus 2x plus 4, and set that equal to 0, you can complete the square, you can use your quadratic formula, but either way, we're going to find that there are no real zeros, no real solutions to this equation, and therefore x equals 2 is our only critical number. All right, that's our critical number. So now the next job is to figure out where is the function increasing or decreasing, and the way we do that is by solving an inequality. Right? A function f is going to be increasing if the derivative is greater than 0. So how do we know where that happens? Well, let's look at our derivative. we would want to find out where 4x cubed minus 32 is greater than 0. And since we've already done the work of factoring right here, 4 times x minus 2 times x squared plus 2x plus 4 is greater than 0. Since there's only one real 0 right here, we can plot this on our number line and test whether or not this inequality is positive or negative, either to the left or the right. Well, if we choose a number to the left, let's try x equals 1 as our test. Well, at our test point, x equals 1, we get a negative value here for the first value. If we put in a 1, we're going to get 1 squared plus 2 times 1 plus 4. That's positive. 4, of course, is positive. And is that greater than 0? No, that's negative. But if we were to try and test a value to the right of 2, let's say at x equals 3, we'd see that, well, 4 times 3 minus 2 is positive, times 3 squared plus 2 times 3 plus 4, that's positive. So it's true here, that is positive at x equals 3. So if we check this out, where do we say the function is increasing? Looks like the function is going to be increasing on the interval from 2 to positive infinity. And likewise, if we were looking for a decrease occurred wherever f prime was less than 0, and we know that decrease, as we showed in the last step, was true on the interval from negative infinity to positive 2. So we've got this function that we know now is going to decrease on the interval from negative infinity to 2, and it's going to increase on the interval from 2 to infinity, where it changes from decreasing to increasing. Our rule says change from negative to positive has a relative minimum. So we have a relative minimum at the point x equals 2, f of 2. Well, what is f of 2? Now we need to go back up to our original function. F of 2 is going to be 2 to the 4th minus 32 times 2 plus 4. Well, 2 to the 4th minus 32 times 2, 32 times 2 plus 4 is actually the same thing as saying 16 minus 64 plus 4. 16 minus 64 is negative 48, and negative 48 plus 4 gives us negative 44. So the relative min occurs at 2, negative 44. Well, that's what we're looking at, and we're done.